forgot to press the button, you know, the recording button. So system responses. Today is about system responses and the spectrum analysis. First part looks similar to yesterday's exercise, where you have a block diagram or flowchart, and basically you just need to analyze that one and figure out the system coefficients A and B, and that is your system. Second one, you calculate the impulse response. Impulse response, brute force method. Brute force meaning you have the parameters B and A for the system. So that system is defined by that. You have the impulse, and you actually calculate the impulse response. Okay, the system linear time invariant system implementation in Octave or MATLAB is called filter. Because most of these systems are filtered. And you just use it like that. Filter system coefficients B and A in this order. So basically, system coefficients for the forward part and then the feedback part. And then the data. Very simple to use, as long as you have linear time invariant system. And this gives you the nice impulse response. And then you basically just check if the impulse response, okay, this is nth order system, meaning what is the highest polynomial number, meaning how many terms you have on those, -1. And if the order number is n, then the impulse response actually either stops here or continues. If it's continuous, then it's IIR. If it stops, then it's FIR. Group delay. How to calculate the group delay? Oh no, derivative. Well, there's a function to calculate the group delay. Group delay was the I could have actually used the different order here, but anyways, it seems that like that. We have the system coefficient, so now we can actually calculate the group delay also, meaning the phase shift, derivative of phase shift. Maybe I should actually change this. Well, it does not really make any difference. We can calculate this separately. As long as we have the system coefficients, we can calculate all sorts of stuff. We already had the zero pole plot. That in Octave is actually just z-plane and those same parameters B and A. I think we have already had this yesterday. Same coefficients B and A. We have the frequency response. Frequency response has two parts: the amplitude and phase response. Amplitude response, for example, like that, and then the phase response, something like maybe that. Okay. Again, same coefficients. and some parameters. Okay, so we use the same coefficients, system coefficients, also to analyze the frequency response for the system. Same thing for the group delay. I think the group delay was called GRP delay or something like that. I need to check it first, but anyways. So group delay meaning the time delay through the system. So this is actually time, and this is the frequency. So in this case, I think something, well, we'll see what it looks like. But the group delay, I think it's group delay like that one, but well, we will find it out. And those are mostly just graphs what you will be doing, and then think of the points like at which frequency the system has highest attenuation and such kind of things. Okay, I see there's again. Okay, now it actually looks better. Then the plot frequency response was the scale the system. Okay, scaling the system. As soon as we can calculate the maximum gain. So max G is here. Then we can simply scale or rescale the system. If you need to scale the system, you basically can scale it to unity gain. Well, just replace B is BB divided by maximum gain what you measured. Brute force. Then you have unity gain. Nothing fancy there either. Okay, that's the system analysis part. And that's the system, response for anything. So basically, just like yesterday, we filtered the sound sample at the last point. So the same system, we just need to know the system coefficients B and A, and what is the input to calculate whatever the output is. Okay, for example, for the delta function, the step function, whatever. For delta function, if you put delta function in, then you know that you get the impulse response out. Period. Just plot it, that's there. If you want to calculate the zeros and poles, that's Z-plane. That does it. Frequency response is calculated by calling Frigg's function. Group delay is, well, that's I have to check. It might be just mark it question mark if it's called that or not. Okay, so yeah, nothing fancy there, but this is important in sense of understanding how the system behaves. Okay, the second part is the spectrum part. There we have a generator sound sample which consists of, well, those parameters. It has a sampling rate, 1.1 second long sample, chirp signal. That's up to you if you want to use a chirp generator, or do you want to try your luck and do the chirp yourself? Start frequency, end frequency, then some random noise in decibels again. So compared to your notes on the first exercise, how to translate this one into the noise variance. So that's basically just to generate it and save it. Then calculate the spectrum of the last data points. Okay, meaning taking the data and basically, whatever here, taking the last data points, not the first ones. And calculate the power in decibels in linear frequency scale. Okay. And then spectrogram, which is thus calling a function. Simple. Okay, it says octave use spectrogram. That's an old-fashioned program, the routine to calculate it. We may need to check the parameters, how to call it correctly. Then filter your sound sample with the system. Okay. And let's see what it looks like in Octave. There. Where shall we start? We start from the beginning. So defining a system. Yesterday we probably had some systems. Did I have second order system? Well, I will just, swing it. Just as a curiosity, what I could show you here, it has no relevance to the exercise whatsoever, but another way of defining a system. I have been drawing this. I have been drawing these zero pole plots and saying, okay, that's a low pass filter. How about if I prove now that this actually is a low pass filter by turning this into the parameters. Now I need to take. So I have zeros and poles. How to turn those back to the system coefficients. So my starting point for this tutorial is that we know the zeros and poles, because I want a filter which has total blackout of the signal at that frequency. And let's make this a little bit more realistic and put, say, my sampling rate is 2000 samples per second. I shouldn't use hertz here, so it's not the same. But well, actually, this would be correct, 1 over a second. Yeah, 2000 samples per second. Which means that this angle here is, the full angle is 1 kilohertz, and that angle is 750 hertz angle. Then I would put here on this angle pole and a pair for it. By the way, in order to get real values for the system coefficients, the zeros and poles must be complex conjugate pairs or on the real axis. That's the only way you can get real numbers to calculate. If you have, say, single zero here, then you would have imaginary values for on this system coefficients. No good, no good. Imaginary values are used only on the frequency space for calculations. Okay, so 0.5 and that's 0.5. That's minus 0.5. So this is the imaginary axis. This is the real axis there. And then that, okay, this angle here is 250 hertz angle. Good. Yeah, 250, 500, 750, 1K. And actually back to here it's 2K. So full circle is the same as sampling rate. Okay, good. How to define these and put it on the octave. So basically we define the zeros first, so we will put those zeros at 750 Hertz. So let me first omega 0. Actually, maybe I can actually just use the angle for 0 would be 2 times pi times 750 divided by sampling rate, 2000. Yeah, that's the complex angle for corresponding to the this frequency. There. So the 0, that single 0 here is on unit circle at angle J times omega Z. There we go. Yep, looks quite familiar values, so it's minus 0.707 something. So it's 1 over square root of 2, right? Yeah, it's as it should be. Okay, and 0.70711 I, so it's complex. And then we add a complex conjugate pair. And the easiest way of doing it is we replace Z by Z, make this one a single column vector. The signals are, and these system coefficients are, single row vectors, but to separate those from zeros and poles, we actually use column vectors for these zeros and poles. And complex conjugate is simply conj CZ. And let's see what it looks like. Yeah, there we have complex conjugate pair, plus and minus on the imaginary. Good, that's our zeros. Next, the poles, same way. Poles. Omega. Well, I'm not putting the omega here since I have the coordinates, Cartesian coordinates. So I have the poles P equals 2. Okay, 0.5 plus 0.5 times I. It's either I or J, either or. It doesn't make any difference. I think I used J on the exponential, I used I here, but they are the same. As long as you don't destroy. Remember, if you use I as your variable, you just lost your complex numbers. Seriously, this is so stupid, You can overwrite all the functions and all the stuff. It's built feature for a reason. Mathematicians sometimes want to, redefine stuff. All right. So, and then the complex conjugate pair would be 0.5 minus 0.5 J. Okay, there we go. So that's the pole, zeros and poles. Let's see what it looks like. So we can call Z-plane, hopefully, Z and P. Does it find it? Or do I need to? I need to load the package again. Okay. Package load signal. Okay. If you don't want to load these subroutine packages, actually you can edit the Octave RC file that it automatically, every time the system starts up, it automatically loads whatever subroutine libraries are you using. Okay, packet load signal because, well, yeah, there. Z-plane. Now I have the Z-plane, and yes, it's on just on my other window here. There. Looks quite the same. Maybe even better looking than in here. Maybe. Okay, real axis, imaginary axis, zeros on the unit circle, poles there. It would be nice to have also some crosshair there, but markers for the axis. Oh, they are, but they are not showing up. Yeah, that has better resolution there. Hmm? Yes. You want to? Yeah, you want to do it? Excellent. You can do it. Okay. Yeah. Actually, let's see. I think it might actually help. Just under that one, you can change the marker size. Otherwise, all of these are objects, meaning that you need to go and get the handle to this object, which is actually called current graphics. Then under that one, there's a children, which is current the axis, and under that there's children for the plots. But you can actually have been doing that one, but yeah. I should actually write a subroutine to go through the. Well, let's see. Does it have any? No, it doesn't have any. Let's see. Select. Can I actually do anything for this? No. No. No, it doesn't actually allow me to do anything for it. So, yeah. But yeah, there's a way. I can show you it, at some point. But now let's concentrate on the, just getting things done. So Z-plane, excellent. How to now? I still have just these zeros and poles, but actually how to convert this into system coefficients. So if these are the roots of the polynomial, then actually there's an inverse operation called poly. So system coefficients on the polynomial coefs for roots. Okay, there we go. So we have B is actually the polynomial coefficients defined by the 0 points there. Okay, those are the coefficients. And then the AA is the polynomial coefficients defined by the poles. Poly. Nice. Wow, that's a perfect, almost perfect filter. This can be calculated quite nicely with a high accuracy. Well, this might be on the fixed point precision, might do some trouble. But anyways, nice and symmetric. Okay, so what next? So the next step would be to actually do some maybe impulse response, frequency response, group delay. We already did the Z-plane, and then the amplitude response. Okay, let's start from amplitude response, for example, or frequency response. BA, this will give actually the frequency response in normalized frequencies, meaning times pi radians per sample. Okay, if you want hertz, the real frequencies, then you just need to call, this one with a couple of more parameters. The next parameter would be the number of points to do the calculations. For example, 1024. And then the fourth parameter, sample rate. Those parameters. So basically, the check the usage for, oops, what happens? Oh, FS. Oh, yeah, I don't have the FS. Yes, 2000 hertz. So yeah, now we have frequency in hertz. So if you know your sampling frequency, then use it on the all of those plots. Frequency response plot, 2000 hertz gives you the Nyquist frequency for the half of it. Yep. So 0 there, and we have the notch somewhere at 750 hertz. Excellent. And we have some gain at 250 hertz. Nice. Just like I designed. And it has, okay, overall gain is something like 18 decibels. So this is not unity gain system. It has some gain on the filter. It's okay if you need the gain on the filter, but usually filter is just filter. It just does the filtering and have the amplifier somewhere else to do the amplifying. So now we can rescale the system to unity gain. And actually what we can do, we can calculate with the same frequency command, we calculate the max G equals maximum of absolute value of whatever this function is returning us. So actually, if there is an output argument given for this function, then it returns the complex frequency response. It has the amplitude and frequency, amplitude and phase information. So we take the absolute value of that one. So that's actually amplitude response. And then we take maximum of those numbers. That's the brute force maximum gain. There. So maximum gain is 8.3630. Yeah, about 18 dB. And the rescaling of the filter is very simple. You take the parameters B and divide it by maximum gain. Yeah. So that's overall gain for the system. To put it, make it a unity gain. And there we go. Wow. Ooh, ugly. Maybe I should zoom it a little bit. Where's the zoom? Where's my? There we go. Oops. There we go. So stop band attenuation about 30 dB, unity gain on passband, cutoff frequency somewhere there around maybe 350 hertz or something like that. Okay, looks like a low pass filter. What do you say about the phase response? It's non-linear. Non-linear phase response. Linear would look like exactly like a straight line. Actually, it looks like a straight line, right? Okay. So basically, the next step would be calculating the group delay. Maybe the same parameters as for the frequency response. We'll see. Okay. Group delay seems to give me just the those values. So GRP delay DD equals group delay. In MATLAB, group delay actually gives you the graph. Okay, they are different. This is not MATLAB. Octave is not MATLAB. It just, it just understands some of the commands of the MATLAB, but it's still not the same. BBAA. Setting group delay to a singularity. Oh, wait a minute. Okay, let's see what did it give me. Plot DD. What does it look like? Okay. So it's just the upper graph. Lower graph is still the phase shift. And this is now actually calculated 512 points. Or actually 1024 points, but this is not normalized. So this is 0 and this is the Nyquist frequency. This is just the point where it was calculated. Okay, but anyways, that's the group delay in samples. Meaning, okay, that warning here actually comes from the singularity, meaning divide by 0 at the notch. At the notch, meaning you are exactly on that point. You cannot actually calculate the phase. There is no phase on a signal that does not exist. Okay, so basically, but anyways, we got a graph for group delay. How to fix the well, maybe that will be just enough. So, but anyways, when you calculate the group delay, when you get y-axis as samples, delay like that one, and then any scale here, that'll be fine. That'll be fine. Good. That was group delay big picture. Just need to calculate it. Calculate like that. Good. So, impulse response. Hey, I didn't calculate the impulse response yet. You can do it. So, impulse function goes in, impulse response comes out. On Monday exercise, there's impulse. Yesterday's exercise, there's a filter. And today's exercise, the filtering. Okay, filtering the impulse gives you impulse response, and then you plot it. Okay, that's the systems part. I will continue now for the the spectrum analysis, since that's quite simple also. I'll just go and take first yesterday's let's see, open. What did I do yesterday? I think yesterday I had some signal generation. Oh wow, I have some signal generation. So that's my signal, and I even filtered it. No, I didn't filter it. My thing. Oh, it was went to my thing. Okay, my sig. Okay. That's my signal now. I just evaluate what I did yesterday. There I go. So that's my sample. Yeah, the last one was my sample. I will do the spectrum analysis for my sig. Or, well, we can also run the filter now. My filter actually. Hey, that'll be fun actually. All right. So what does the filtered? So I have a low pass filter, which should be much better than the yesterday's 4-point running average. Was it? Let's run those one by one. Maybe. Still a lot of noise there, but anyway. So not non-filtered data and filtered data. Let's do some spectrum analysis. First, a single spectrum comp of 1024 points on the beginning of that signal. So I take a subsample. Since we have 44,000 samples in my full signal, it's 1 second long. It's quite long. So I want just the subsample of 1024 points, which actually should give me spectral resolution of SF divided by 1024. So this is the spectral resolution. So basically the Fourier transform just transform as many data points you have selected to and divide those into as many frequencies on the frequency space. Okay, so my frequency resolution for the spectrum is 43 hertz. Enough for me. Okay, so frequency resolution equals about 43 hertz. I take the subsample now, which was FM y sig 1 to 1024. Those are the first values. You need to figure out yourself how to calculate the last values. But the following would be the same. You first do the Fourier transformation. So that's the Fourier transformation using FFT rotate. And then basically the power spectrum PSS power of that signal is actually that FSS multiplied cell by cell with the complex conjugate of FSS. Another way would be calculate the second norm. That would be the same thing. But this is the power spectrum. There. What else we need? Well, it would be nice to have a frequency scale. So the frequencies actually there are the following: from 0 to 1023. So 0 frequency included, divided by 1024. So that's normalized to 0 to 1. And my 1 actually is the sampling rate times Fs. So that's my corresponding frequency axis. So now I have power axis and frequency axis. But this is not power yet. If you calculate power spectrum, this should be transformed into decibels. dBPSS equals 10 times log of 10 of PSS. So we already have power in linear scale. We just need to translate that one to logarithmic scale. Okay, as you can see, I don't have the reference power here. I could have it, but it's in basically logarithmic scale is always relative scale. It doesn't need to be there. And I don't have the absolute the calibration of the system either, so it really does not make difference. Okay, then I can plot FF DB PSS, and I will get too much information. I get from 0 to sampling rate, but I need only this half. Sorry, that one remains there since there's sublot, so let me clear the window and do it over again. What happened? Close the window and plot it again. Yep, there. Come on. There we go. So basically this is from 0 to sampling rate. We need only the half of it. Okay, so let's plot it again. Either zoom it or plot it again, but I like basically there. So plot FF from 1 to 513 to dBPSS 1 to 513. So basically the middle point, the Nyquist frequency, is the n over 2 plus 1 because of the offsetting. We started from 0. Okay. There we go. So only thing is missing here is the axis information. So X label frequency in hertz, Y label power in dB, and a title single power. And what we can see, there are 2 peaks here. How did I actually make this signal? It had some, okay, let's zoom that part. So it had a 440 hertz signal, then it has the first harmonic, so it's 881. I don't have enough of spectral resolution to say it's exactly that 882 hertz here. Then we also have this noise here. So noise actually appears as these spurious peaks on the spectrum. The low-pass filter part actually shows up here. So without the low-pass filter, we would have the spectrum just continuing like that. You can try it yourself if you don't believe me. But anyways, so that's after the filtering. We have suppressed some of this noise on the non-interesting part of the spectrum, and we haven't touched much actually these tones. Good. So that's a simple single spectrum. Next is this. See what the spectrogram looks like. Okay, I need to check the help on spectrogram since I want to see. Yep. Okay, this is also missing one parameter. So what we are using actually is this plus sum. So at least that form. Let's try that one first and see how many parameters we actually need. Since at least MATLAB gives the axis, the reverse order, it gives frequency on horizontal axis and time on vertical axis, which is total bogus. It's not, you know, in no culture time never starts from the bottom and rise up. Never, ever. I would actually understand if they made this kind of waterfall system. So basically, time starts here and then the death goes like this, but it has the reverse order. That's what you get when you give non-engineers too much power to decide what kind of graphs to make. All right, but anyways, let's try this form. So, signal number of points in the FFT. So this is actually how many samples we take for each Fourier transform, then the sampling rate, and then some magic. But let's see first. Quit. Yeah. So Spectrogram. What else white signal name? F my sig. Okay. 512 points is enough. That would produce 256 points in graphics. Okay, 256 pixels. Then times basically how many parts you got this one. And then sampling rate 4.44.1. Let's see what does it look like. Yeah, this is correct. We have time here and we have frequency there. Excellent. We don't need to. So if you use MATLAB, you need to swap the axis every time you call the function. Okay, so basically time goes there and the frequency goes there, and it's very non-interesting picture since there was no change in those tones. The only thing that changes is the noise. So it's random. You get this kind of noise speckle there showing up. But for the chirp, what you are expecting to see is from start frequency to end frequency aligned like that. Okay, good. That's the lab tutorial, and let's see, lunch break until. So I will be back around, say, 1:30 at latest. You can be back here earlier and start working on the exercises. There we go.